couple of examples of geometric sums or summations. Let me just review the master formula real quick. If you have the sum of a geometric sequence, so here's if you just put commas in between these, these would be a geometric sequence with common ratio r. It's really crucial, starting with first term a1. So it's a1 plus a1r plus a1r squared all the way up to a1r to the n minus 1. Now that's a typical way to write the nth term. It's the most common way to write the nth term of a geometric sequence. And it's basically because of our conventions of how we count that that's an n minus 1. If you sum those all up, amazing magical thing that happens is that is very closely related to the next power of r, the next one after the one you used last. So you subtract 1 from that, divide by r minus 1. That would be the result if you started from 1 plus r squared to r to the n minus 1. And if you have a common factor of a1, some first term is not equal to 1, you just have to multiply by that. You'll often see it in this way with the subtractions reversed top and bottom. They're both totally equivalent to each other. You might also see this summation written with the sigma notation, and the way to package that, you'd see that as the formula a1r to the k minus 1 with some temporary dummy variable k, and then that's going to go from 1 usually to an ending point n. And in other videos I have some examples where there's some variations in that. Okay, so for example, see if I can just squeeze it in here before I have to erase all the general stuff. Suppose I had 5 plus 10 plus 20 plus dot 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 plus let's say 5 times 2 to the 9th. Okay, suppose we had that written out. And this is kind of nice that it's written in exactly a form that seems to indicate the pattern. Well, you want to check that it's really a geometric sequence. Do not use this kind of thing if it's not geometric, but yes, times 2, and then it looks like we have that pattern, and indeed, it's the first term, 5, times powers of 2. Looks good. Okay. So the question is, what's going on here? Well, we need to just figure out what's A1, what's R, and what's N. And then we're just ready to plug into the formula. Well, A1 is just always going to be the first term, so that's going to be 5. The ratio we figured out is 2. If you don't know the ratio, then you probably haven't checked carefully whether it's geometric at all, and you shouldn't be using this yet if you're not sure it's geometric. The N can be the tricky thing. The N has various interpretations. For one thing, if it's written in this form exactly, it's just how many terms there are in the sequence, which we've known for a while now is really important to know for any kind of summation, just how many things you're summing up. But that can be a little tricky because of the dot dot dots, okay? But you can also do some pattern matching. The N should make a match with this. Okay, so 5 times 2 to the 9. I'm not doing the sum yet, I'm just analyzing the terms, which is very, very typical again, is supposed to be, okay, A1 times 2 to the n minus 1. I'm just matching this guy. So really, I see that n is going to be 10. Okay. And that's not surprising because, again, the key is that what should show up in the summation formula, the cumulative result, should be the next power of n besides the one we have here. So that's why we're going to get 5 times the next power of 2. So the n here is 10. That's the next power of 2 divided by 2 minus 1. And the divide by 2 minus 1 is nice. Let me just make a little more room. Well, that's just 1. Okay, that's a nice thing about summing up things where the ratio is 1. And I just get 5 times 2 to the 10 minus 1, which is 1,023. And that's 5,115. Okay. Now, there's only 10 things here. It wouldn't have been impossible to sum up all 10. But if there was 100 or something like that, this is a major shortcut. Okay, so that's one example. Okay, let's see. I kind of want to keep that. I shouldn't have left so much room. Let me just tighten that up a little bit because I want to use the summation notation in the next one. This can also be written some k equals 1 to n, a1 r to the k minus 1. Okay, same deal. Okay, so now let's suppose I have it given in the summation notation. Let's say it's the sum k equals 1. I'm going to do another one that's pretty small number, where you could do it by hand if you wanted to. K equals 1 to 6 of 6 times minus 1/2 to the k minus 1. So this is nice in that it's written in exactly the standard form. And again, in some other videos, I talk about what happens if it's not in exactly the standard form. Well, so a1, well, and the other thing about summation notation, if you're ever confused about summation notation, unpack it and convince yourself that you know what it is in the dot 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 form. Okay, so when k is 1, this gives 0, this gives 1, and you get 6. And that should be, if it's in the standard form, you should be looking at a1 right there. Okay, now when k equals 1, sorry, k equals 2, you get the power is 1, so 6 times minus 1/2, so you get minus 3. Okay, when k equals 3, you get minus 1/2 squared, which is a fourth, 6/4, that's 3/2. Okay, it looks like it's alternating in sign. When I take a negative number and take it to higher and higher integer powers, you get alternating sign. Okay, and there's not many dot dot dots to hide, but when k is 6, I get minus 1/2 to the 5th. That'll be negative 132, 132nd, and that's going to be minus 3/16. Okay. Again, it wouldn't be impossible to fill in the dot dot dots and add that up, but let's see what our formula gives us. Okay, so a1 is 6. That's either from there, because it's in the absolute standard form, or more certainly from there, it's the first term. R is always what you're taking to higher and higher powers. So it's a little bit more work than you really need to do to expand this out and then take the ratio and realize, oh, that over that is minus 1/2. That over that is minus 1/2. Oh, that's not a coincidence. It's always this thing. Whatever you're taking higher and higher powers of, that's the ratio. And it's not this whole thing, it's just what you're taking higher and higher powers of. So again, because this is in a very standard form, you can really read it off. Okay, and then n, the nice thing here, because it's in the standard form, starting with 1, ending with 6, there are 6 terms, or the last power you take of this is 6 minus 1, so the n here is 6. Okay, so now we're ready to put that in, so it's going to be 6 times minus 1/2 to the 6. Notice the highest power that actually appeared in the sum was minus 1/2 to the 5th, but in this case, it's the next one, and then over minus 1/2 minus 1. Okay, now I'm using that form. Often, this is where the other form is slightly more convenient. Doesn't really matter too much. 1 minus minus 1/2 to the 6th over 1 minus minus 1/2, so that's 1 plus 1/2. Okay, so 6, let me just do the 6 over 3/2 here, separate, and then 1 minus, and then minus 1/2 to the 6th. Well, the minus sign goes away because it's an even power, and so that's 1 minus 1 over 2 to the 6th. So notice that's getting pretty small. It's mainly just dominated by the 1, and that's going to be really important. So 6 over 3/2 is 6 times 2/3, which is 4. And then 4, and then I'm going to distribute it out. 4 minus 4 over 2 to the 6th. There's a little cancellation that happens there, and I know I'm squeezing it. Let's not squeeze it. We're going to get 4 minus 4 over 64, 4 minus 1/16, or 3 and 15/16 if you want like a mixed number or something like that. Okay. Or if you want, it's 63 over 64, looks like. Okay. So, 63/16, my bad. 63/16. Various ways you can write it. Okay. Um, okay, um, so either if you could get it, if you have it this way, or if it was written out this way, I hope that gives you some good examples of how you would get the summation. And we're going to play with this and get some interesting consequences out of it soon.